Before we begin here, let me check quick. What is DC-DC converter? Do you have any good definition? DC-DC converter is just a power converter which changes DC value from one to another, right? Everybody knows that, then why you're not speaking? Feeling too shy, it might be silly definition, but that's the actual definition. DC-DC converter is nothing but a power conditioning circuit, right? Which changes the level of DC from some either low or it goes to high. For example, from 12 volts you can go to 24 volts, or 12 volts you can come to 5 volts, or whatever it is, right? Now, one of the very interesting topics these days in DC-DC converter world is about how to understand and control conducted emissions, because that's giving nightmare, and those nightmares get transferred to your nightmare. So my request is, if you are not directly connected with DC-DC converter, it's fine. But definitely in your company, you will have colleagues who would be working on these DC-DC converters. So once you meet them, maybe tomorrow, day after tomorrow, next week, tell them we have seen something nice in DC-DC converter. If you have a problem, just link them to us. We will have solution, because we know this problem is very real. Most of the people working in DC-DC converters are facing these issues. So let's talk about it. Very quickly. So one of the biggest challenge in DC-DC converter is to handle this EMI. The high-speed power converters are producing noise and EMI that can interfere with other electronics and degrade the performance. Either your performance or the nearby electronics performance. The layout parasitic can be a dominant effect and a costly contributor to EMI. In case of SMPS, so switch mode power supply as you call it. Now whether you call it DC-DC converter, SMPS, some people call it EPC, some people call it power converters. There are many names by which a division can be known inside an organization working. So the problem currently is it's not easily understood or predicted. Right. So using modern integrated tool sets, you could not only simulate the conducted emission as well as check the compliance upfront. You don't need to wait for your electronics to fail in the real world in order to understand. So let's see what it is. So four main topics: understanding the EMI characteristics and noise mode. How do we measure conducted emissions? A design process which is proposed, which is EMC compliant. So if you follow that process, probably you will not have the EMI or EMC issue in the real design. And then we'll give you a real design case study. So this is a real customer design case study which I'm going to present, just following the same process. Okay. So EMI, everybody understands EMI? Anybody here don't understand EMI? Previously, digital engineers never used to understand EMI. Now even they understand EMI after coming to gigahertz range, right? So everybody understands. Interference of electrical circuit through an external source by conduction, either electrostatic coupling, electromagnetic induction, or what you call as radiation. Now, interference can degrade or totally stop appliance from operating. And sometimes that can be life-threatening, especially if you look at automotive sector, space, defense sector, computing, medical electronics, and so on. So EMI can be life-threatening not for others, even for yourself. So it's very important. Cases of medical electronics, imagine some operation going on, very critical condition, and then you have an EMI, you can't really communicate, and your instruments can't function properly. It can be life-threatening. So it could be, it's one form of unintended transmissions. Yeah, and unintended transmissions can happen in two ways. You can have radiated emissions, and you can have conducted emissions. Now with the power electronics, radiated emissions are of less concern. They are of concern, but less concern, because the frequencies are not that high. Right? If frequencies are not that high, you don't have enough resonant place in order to have that to happen. Conducted emission is more problematic for them because it's a contact-based, physically conducting contact. It's not only you. It can be through wires, can be through some grounding issue, due to some earthing issue. It can happen from anywhere. So idea is you have some kind of conducted emission which is happening. Four main coupling mechanism, of course, radiative, capacitive, inductive, and conductive. So you have a source and you have a victim. That's the whole scene. Between them, four of these conditions can exist. one of them or more than one. In power electronics, you have capacitive and conductive, which is the two most problem creating. So you have capacitive coupling and you have conductive path. Yeah? So those are the two main causes. So when you look at EMC's ability for an instrument or equipment to function satisfactorily in its electromagnetic environment without introducing any additional noise or interference to the other equipment. Yeah? Okay. Right. So some key regulators. So depending upon which part of the world you belong to, there will be one of the regulatory body who would be monitoring this. Your systems have to certify to those standards in order to be used or sold. Yeah? So if you look at harmonics, they are major contributor to EMI. But traditionally, power electronics guys have always been seeing, these kind of waveforms. So this waveform is the same signal. It's a 2 megahertz pulse with a limited harmonic content. So if you take a 2 megahertz pulse and only consider two harmonics or two Fourier components, you get this red half sinusoid kind of waveform. Yeah. So guys sitting here. So red half sinusoid. Then this orange or magenta type color is 5 harmonics. Blue one is 5 harmonics. This orange type color is 10 harmonics, and this blue type color is 50 harmonics. So even with 50 harmonics, your pulse is not clean. You still have some niggling going on. So this is one way they look at the problem. But looking at this signal, can you tell what's going on? Which frequency content is causing the issue? Very, very difficult. Yeah. So if you look at harmonic response of that or a frequency response of that, amplitude versus frequency, you can see all these switching noises, spectrums, peaks very, very easily. You know exactly what's going on at what frequency, how much power is available at each frequency. And typically this is how the specs are formed. So if you look at certain classifications or certain regulations, like for example this one, CISPIR 25 class 5. So these are the total noise which is allowed versus frequency. These red bars are the limit lines. And these are the emissions coming out of your electronics. So as long as you are not crossing that limit, you are okay, right? You should be below that limit with some margin. Now noise modes, so if you want to understand it further, if you go to noise mode, look at the noise and see where the interference is coming from, due to which region or due to which reason it is getting produced. You know how to fix it. You can decide how to fix it. Okay, so before we go in, so when we say noise mode, how many type of noise you can have in your system? Everybody give answers, so I can't. Probably you saw that in the slide. You guys have good idea. So two noise modes can exist: differential mode noise and a common mode noise. Now, both of them will have different characteristics. Both of them will have different suppression techniques depending on what's applicable for your system. So, differential noise is a common case. All power converter produce this noise. Current flows in opposite direction. We all know, right? Common mode noise is more difficult to understand, but it's not magic, by the way. Yeah? But some people, call it magic. Current flows in phase from direction from power source to ground can be difficult to isolate and trace down the root cause, because you really can't find where the origin of this was. So you have to somehow suppress the noise. Yeah? But usually it is caused by capacitive coupling and a physical parasitics. So physical parasitics can arise from either the components which you have used in your circuit, or it could be arise due to the layout which you have done, effectively, which is giving rise to those parasitics. Okay. So I'll just skip some of these. So if you look at closer look at the noise modes in a compliant design. So right now these noise, this is differential noise, and the red one is the common mode noise, and the blue one is differential mode noise. So as long as you cannot have zero noise for sure, but as long as your noise is below the threshold, which is not causing an EMI issue, that's okay. So you need to just contain the noise below a certain threshold level. Okay, now here is what happens in real life. Yeah, you set up your circuit, you simulate your power converter circuit, you look at the schematic response, look at the noise response, everything is beautiful. Yeah, no ground, common mode currents. This is with little ground spiking is seen at the schematic level. So you go ahead and your schematic doesn't produce any so-called EMI, kind of effects. You go ahead and fabricate your PCB, you populate your PCB, assemble everything, and you test. And that's what you end up seeing. You see these huge spikes coming up in your power converters. Now, these spikes can be as high as 10 volts, by the way. Right? Now, if you look at layout, so this was with all schematic components. Now we look at the layout, you suddenly see a higher level of common mode noise. Differential is more or less okay. When you look at the red waveform, then the common mode noise is much higher. And that's predicted by the layout, but not from the schematic. I'll tell you the reason why it happens. Yeah. Now, why all these things are becoming, layout is becoming more important. So power electronics is probably going through the same phase which high-speed digital guys went through maybe 10-15 years ago. When people suddenly woke up and realized, I can't do the layout same way I was doing it for 50 Mbps or 100 Mbps kind of data line. Now I'm routing 2.5 Gbps, 5 Gbps, 10 Gbps. What happened? How many of you are from digital background here? High-speed digital, I see a few familiar faces here. So what changes? If you are routing it for 100 Mbps signal and you are routing for 5 Gbps signal. Transmission line effects, parasitics, vias, reflections, suddenly everything becomes important. So in 50 megabits per second, probably you can close your eyes, take your pen and draw anything on the layout and it will work, right? That's how it used to be layout design, with minimum fuss. Yeah? Now everything is important. People are hiring PhDs to solve a simple VIA. They say, give me VIA which works up to 50 gigahertz, and PhDs are creating those VIAs which works up to 50 gigahertz. Right or wrong? Yeah. So it becomes all electromagnetic science. Same thing is happening now slowly with the power electronics. Do you know why? What's changing in power electronics? Higher inductive effects caused by switching frequency. Switching frequencies are going higher. Why?
Because they want to reduce the size of the comp.
Absolutely, perfect. You deserve one. Can you help me? Yeah? So higher switching frequency because they want to reduce the size of components. Why is that? Why would you like to reduce the size of components? System size is reducing, so your power converter has to go down. That's one reason. Which is not the only reason. Why again? Huh? Portability. Less power consumption? No. They are power producers. Efficiency. Yeah, he deserves another one. The orange type shirt, striped shirt. Raise your hand, please. Efficiency is the main criteria. You need higher and higher efficient power converters so that you can utilize the maximum available power. You think about battery operated vehicles, electric vehicles coming in. You have a limited power. How much can you utilize? How efficiently can you transfer before you go for a full recharge and stuff like that, right? So a lot of effects coming into picture. Size is one, efficiency is one. Within the same form factor, I was producing 400 watt. Can I do 800 watts? Because now your systems are getting complex. You have a lot more FPGAs, a lot more systems, right? So the demand for power is going up. System size is reducing. You're not expanding. Yeah? So all these factors are driving up the switching frequencies. Higher switching frequencies meaning the layouts are becoming that much more important. Now with higher switching frequencies, anything above, let's say 100, 200 kilohertz of switching frequency, you cannot just close your eyes and draw the layout. Each and everything will matter. You'll see how. Yeah. Let's quickly go through how typically you measure the compliance. So radiated emissions. Typically you have a MXC kind of box and you have an EUT. You have a reference antenna. You measure the radiation and you check. You check for electric field strength. You check for magnetic flux density. That's what they do in radiated emissions. In conducted emissions, they have electronics under test. They have the mains, the actual DC source, and you put in a listen, and a talk about listen, and then you have a limiter and you feed it to the instrument and you measure the conducted emission. Units are different. The commercial guys measure dB microvolt, the military guys measure dB microampere. So these are the two measuring units of that. So conducted emissions will conduct through wires, capacitances, and that's quite challenging for SMPS guys. The main SMPS frequencies are not very high and it decreases exponentially with distance. So radiated emissions as of now are of less concern. They are of concern, but much lesser than the conducted emissions, which is happening. Okay, so here is typically how you measure. Sorry about that. So you have an EMI receiver, you have a power source and electronics, you separate them out with the listen so that they don't interfere with each other. It's a known impedance for power source as well as the UT, isolates and prevents the noise generated by UT leaking back into the power source, and that's how you measure. If you have to create an equivalent of that into simulation environment, here's a very simple topology of a listen. You have a supply, you have VDC output, and you can plot impedance versus frequency. So if I have to replicate this process in the simulation world, this is my design. This is an ideal DC source, ideal or non-ideal DC source. So these both I can control. This EMI receiver is already there in the software. I just need to make what? This listen. So I just need to have equivalent, virtual equivalent of this listen. So here is a very simple representation, and this graph is available in all the data sheets, whichever vendor you buy the component from. So you just adjust your inductors, capacitor, resistors to fit in the diagram. It's kind of very simple, not very difficult. Okay. So EMI, why would you like to do that? Because EMI measurements are expensive and are complex. You need to set up a whole chamber, you go to chamber, you set up the whole thing, set up your electronics, do a conducted emission test and all that. You need to have these benches. And then physical location, equipment use, lead length, type of equipment, all that will reduce consistency. You test it on day one, go back after 2 months and you test it again, you will have some variability in your test, testing criteria or testing environment. So you will have a change. So in simulation, it has no inherent test bench limitation. So you could set up these things and simulate it in your software environment and make sure your design is complied to those standards. Yeah? Another limitation from the hardware side, the bandwidth. Now, in order to do a good measurement, you would want minimum noise coming from instruments or external sources, right? So how do you restrict the noise of the instrument? By reducing resolution bandwidth, right? You talk about a spectrum analyzer, resolution bandwidth, you make it smaller, noise level will go down. How small can you do? Because you have to do a frequency sweep. If you go below a certain threshold, it takes a huge amount of time to just do a signal sweep. Simulation has no problem. Yeah, everything is shown as 0 Hertz RBW resolution. So what you see is an absolute clean. Software will not have its own inherent noise added to your signal. It will very transparently show what your signal is all about. Again, few detection methods, and you can build out your own detection methods. So that's how typically you measure. You connect everything together in the recommended configuration. Switch off the DUT and just scan and see if there is a radiation. That gives you the inherent noise in your test setup. Then you switch on the DUT and check for the compliance failures. Where did you fail to meet the compliance limits? And then search for DUT emissions, build the signal list. Find out at what frequencies are you failing, and you build a list of that. And you go back and probably change the detector and remeasure. If even by changing the detector, if you still have the compliance issue, you go back and redesign or modify your EUT or the electronics which you're testing. Has anybody done this kind of testing before you? Yeah, couple of guys. Yeah. Okay. So that's how typical process goes through. Now let's quickly see how can you solve this as a design process. It's all about adopting a new design flow, and everything you can do with very, very high accuracy. So you can identify problem upfront before expensive fabrication, and you can see what will happen if you don't do that. So you have a schematic only, everything is clean, and and you have the layout, that's how the real life will look like, and you will have emissions crossing over. So if you don't want to be in this situation, if you want your layout to work exactly the way it is, here is the thing. Yeah? So you need to understand the harmonically related component, you need to understand the noise mode, especially the common mode noise is what you need to understand, and any instability you may have. And look at the effect. So usually in between you will have, if you have an EMI issue or you have a radiation issue, it will be caused by components parasitic, the inductors, the capacitors and all that which you have used. On a higher frequency side, it will be caused by your layout. So depending upon where you are failing, you can find out or narrow down your search to that respective component. Okay, so I'll just quickly go through. So ways to reduce EMI, simple. Reduce the switching speed. No high frequency switching, lesser EMI problems. Is it practical? No, because it defeats your whole purpose of using a smaller component, less compact size and all. So there is a problem. Another way, even by reducing, your problem may not go away. What was radiating at, let's say, 2 megahertz might shift to 200 kilohertz. So 2 megahertz can come down to 2 kilohertz or 20 kilohertz or 200 kilohertz, but will still radiate at that. So it may not give you the thing which you are looking for. Okay? You can add an EMI filter along with your power supply. Say, what about EMI filter? But EMI filters are bulky, costly, and then remember, differential mode noise and common mode noise will require different type of filtering. So you first need to understand for what purpose are you doing. So you cannot just have EMI filters all over the place in your system. That's not the way. And it's also costly. They're not very cheap. Okay. So here's a typical process. Simple 6-step process. Create a library of components with complete parasitics, so that no component is treated as an ideal component. Yeah? All the components should be there with parasitics. Simulate schematic design, achieve the basic performance compliance. Whatever efficiency criteria, voltage criteria, current criteria you may have, go ahead and design that first. Simulate the performance with layout. Take layout parasitics into account. Don't treat schematic as ideal interconnection between the components. Simulate layout. See how this layout comes in between the components. Optimize the layout to restore the performance in case you see there is a layout parasitic. Something was working nice, just after having layout not working nice, that means it's a layout parasitics which is caused. Just modify the layout. And then if layout modification serves your purpose, good. Otherwise, go ahead and determine EMI filtering or snubbing circuits as may be required. And then you resimulate the design with EMI filtering and get to the optimum response as much as you can. Simple step, here is the flow. So typically what you need from a tool, you need to have a schematic editor, you have a layout editor, and you need an electromagnetic editor. So that's what a power electronics engineer now needs. In the past, people were happy using OrCAD, PSpice, Sabre, LT-Spice. There are many tools if you go around this area actually. But all of them are only schematic simulators. They don't even have frequency domain simulator. So you need a schematic layout and EM simulator. EM will extract the layout phase parasitics. Integrated EM will automate the process. So you don't need to export, import all those files. You need to have a time domain and a frequency domain simulator, preferably. Although basic requirement is only time domain simulator, but if you have both, it's actually very good. Because sometimes if you're looking at 50th harmonics or 100th harmonic, doing time domain simulation can be really time consuming. Whereas frequency domain simulation will do a job in few seconds instead of holding up for a minute or something. So ADS has all these features. So here is one test case study which I'm going to present very quickly. When you do schematic only simulation, these are the waveforms. As you can see, it's kind of clean. You are below your breakdown voltage. The gate drive looks okay. The spurious emission looks okay. So that's what was obtained in a schematic design. It's a customer test case study, actual power converter. When you went ahead and did the simulation with first cut layout, you can see the spikes is even crossing the breakdown voltage limit, which was 30 volts. Yeah? So your output is only 5 volts, and with spikes you are crossing 30 volts. Kind of limit. So dangerous. Gate drive looks little messed up, lot of spikes and overshoot. And if you look at spurious, it's all over the place beyond a certain frequency. I think it's beyond 2 megahertz onwards. Everything is above the limit line which you are supposed to comply to. Then we took it, understand the whole requirement, we fixed the layout and the EMI filter or whatever, and that's the final performance, which looks very, very similar to what you achieved in the schematic. You cannot achieve better than the schematic, that's your golden reference. So idea is to make layout as transparent as you can so that you achieve back the same schematic performance. Right? So here's a design case study. Automotive Buck Converter, 12 volt to 5 volt, 250 milli ripple allowed on voltage, 10 ampere, 2 megahertz switching speed, 80% efficiency required, should be SysPIN class 5 compliance. So these are the design goals which we need to make the design for. Okay, so first step number 1, component modeling. So ADS, we can go ahead and model components with parasitics. That's kind of pretty easy to do. If you have S parameters, you can bring in S parameter. Vendor library models, you can bring in. So very, very powerful in that regard. For power devices, you get SPICE models. For example, in this case, the model was downloaded from Renaissance. So the model was available in download, SPICE model imported into ADS. S parameter models were there in TTK, that's for power inductor, and you have a SPICE model as well as S parameter. Okay. And then you build a first step circuit. This is a half-bridge buck converter. You make up your circuit diagram and you run simulation. Arrange it like this. So these are to listen. This is your battery. That's your input. Those are your chokes, and that's the actual circuit electronics which you just saw here. Although the symbol looks like layout, but the first simulation which we have done inside is the schematic. This is only symbol. That's the schematic inside. You run the performance, everything looks okay, but you have an EMI problem. In the schematic itself, you have an EMI problem. So now, we look at EMI filtering requirement. There can be many filter. So common mode EMI filtering typically is what you use here. Just a skip. And again, these can be with parasitics. You can have S parameter. You can model all of those behaviors. Yeah? All the parasitics. So with no EMI filtering, this is what we got. With bi-section filter for rejecting the common mode noise, you can see everything is pretty smooth. So we are complying. So we went ahead and made the PCB layout. And then if you try playing with filter, there's another type of filter which you can see with physical parasitics. So this is an ideal filter, the center plot with the ideal filter. Ideal inductor, ideal capacitors. The bottom one is with inductor parasitics, capacitor parasitics, and suddenly you can see one nice plot. But again, you're complying to standard, no problem. Yeah? So EMI filtering is doing its job. So that's the final performance. You bring down the compliance, ripple of 95 milli, output 5 volt, efficiency 82%. Design goals are met, complying to your SysPIN, 25. Now, we go ahead and include the stacker and we simulate this PCB. That's where your power components are going to be soldered. The same design which was showing compliance is not showing compliance now. If you can read, what's the efficiency number? 72%. What's the ripple? 300 milli. Whereas target was 250 milli and below. Yeah? And the compliance limit mass are gone. Yeah? So look at, again, different type of filtering techniques to try to reduce. And now, CMF was already there. The common mode filter was already there. Now understanding the layout parasitics. Yeah? So each and every trace will have its impact, and that's what the designer has to take care of. But this is where the education is needed. Now, the impact of the layout is affecting your performance of the whole circuit. So that's the only education. So if you guys are seeing the same problem with your power converter groups, just handhold them here. If you don't want to do it, fine. Invite us, let us talk to them. We'll give them enough guidance and tricks and tips how to handle. So here is the EM excitation. When we say visualization and we try to pinpoint, you can see the hot areas. That's where the maximum current is. Wherever is the maximum current crowding happening, that's where your parasitics are. And that's what probably the loop which you need to break. So how do you break this loop? Anybody else? How do you break this loop here? So when we plot the EM simulation, you know exactly at 4400 ampere per meter peak scale, that's the area which you need to target in order to try to solve the issue. Right? So now we look at what's happening. Why is that area causing? LDI by dt. Everybody understands this equation, right? So higher the L, higher the contribution. Longer the trace, higher is the inductance, right? So you need to shorten this loop, shorten this inductance, and this thing will become okay, right? Now that can happen due to many methods. First, instead of routing a thin trace, make a trace a little thicker. What will happen? RF microwave guys should know that, right? Easily. Inductance will reduce because it will become capacitive types, right? So you reduce the inductance. So you can see here the same voltage with this ripple, with thicker line, the ripple has come down. That's one method. Second, reduce the return loops. Instead of having the ground so far from the signal which is traveling, try to shorten it. Shorten the return loop, your LDI by dt will reduce automatically. Third, use a lower ESL capacitors. Yeah, wherever you see a large transient switching, transients getting generated, use a lower ESL components. It will reduce the ripple. So 3 techniques. We apply that. So instead of using this normal trace, we improve the trace routing, simulated the S parameter and things like that. Now, again, why I want to go back to 10 to 15 years? Because power electronics guys don't understand S11 and S22 and S21, right or wrong? Right? They understand voltage, current, the intermittent switching, the transient, overshoot, undershoot, group, all that. Same thing was there with digital guys. Go back 15 years down the time. Were you aware of touchstone file? Probably very few SI engineers were aware of S11 and S22 concept. Everybody was behind TDR. The whole science was about TDR. Now everybody talking about S parameter, S11, S22, S21. Right? Something similar going on in power electronics industries. So you optimize the whole thing. We modified the layout. Now if you look at layout, current visualization with modification, with the same density, cell, there's no reddish structure here. That means your layout has cooled down, the return loops have gone down, no current crowding is happening. So probably this layout has much lesser level of parasitics, what was there in the earlier layer. So let's look at the response. So performance is restored, design is compliant. You can see efficiency 82%, output voltage. Ripple is 225, spec was 250 milli, now it's 225, so almost there. But still, we can do a little bit of job in improving that. So we included a low ESL capacitors there, and you can see the ripple down to 95. Now, if you compare this spec, it's very similar to what you got in a schematic. So now we with these modifications, we made layout effects transparent. So now definitely this converter will definitely work because we taken care of all the parasitics which might be caused. Yeah. So this paper is right there. It was published in ISEF 2016. Reasonable correlation achieved between measurement and simulation. And you can read all those there on downloading. This is from ROM Semiconductor. You can go and download this paper. Same case study has been described in a little more detail with some formulas and stuff. Alright, so that's all for this presentation. So just to quickly summarize. As you saw, component layout parasitics dominates the EMI issue. Conducted emissions are composed of your differential mode noise and common mode noise. EMI countermeasures are targeted for different noise modes. So you need to first check what kind of noise you have in your system. and accordingly take the corrective action. Yeah. Schematic only simulation is not sufficient because they leave out detail which will limit your accuracy. So you can't really predict what will happen in real life once you make this converter circuit and test it. Yeah. And EM design flow was illustrated in this short presentation to design a compliant SMPS with the specification and CISPR 25 class 5 specification. So I'll stop here and look at questions if there is. Yes, please.
The red colored thing.
Which red color?
Simulation was the trace was red.
Oh yeah, red means current density. So right now, if you look at, so probably you are referring to this one, right? Yeah. So this is like a shaded current plot with 4,400 ampere per meter. So this is like a gradient plot. Blue means cold area, red means hot area, and that's the gradient scale which you are looking at. Peak value of 4,400 ampere per meter. This is momentum. When you run momentum and launch visualization, choose an exciting point, and it will excite on the ports, on the pins here. So based on the inductance calculated or the factors calculated, it will show you how the fields are distributed in your PC. So very, very useful tool. I mean, RF guys utilize it quite a lot. High-speed digital applications can utilize quite a lot if you have unwanted resonances happening. And power electronics now can also see that. Yes, please.
If you have
So to make this simulation work, you need a special EDS spice model, EDS, that will work with EDS, or will if I want to use a standard off-the-shelf or a boost converter, and if I use air, whatever available in spice model or something like that, will it work with this, or you need a different model to simulate this?
No, we can import spice models. We do support P-Spice, Spice 2G, 3G, Spectre, H-Spice, all kind of formats you could import. But in areas to simulate it, you need a time domain simulator.
Sure.
Yes. Yeah. Model can be any format. Yeah. Sorry.
So if you have a requirement of both power electronics and high frequency,
Yeah.
you need to do a thermal simulation and EM simulation together.
You can if you want. So that's one of the topics which I am going to talk about in the high-speed digital session. That's called DCIR electrothermal. So we will do DCIR drop analysis along with the thermal effects on the board, look at the temperature profile of the board and stuff. That's possible if you want to do. Any other last